Welcome back. We've completed the calculus of residues presentation, which was one large presentation where everything went by the same principle. We wanted to use the residue theorem to solve integrals. Well, there are some more applications of the residue theorem of residues, which we're going to talk about in this presentation. And of course, they are similar to each other because they involve residues and the residue theorem, but I just couldn't find any better title than more applications. Let's take a look at what we're going to do here. On one hand, zeros and poles can be used to determine how functions deform certain contours. And that's what the argument principle is all about. So that is something where we're connecting something highly geometric to something algebraic. We can also use these kinds of arguments, meaning residue arguments, to count the zeros of a function inside certain contours. And that is what Roche's theorem is all about. I'm not sure if people ever take the geometry of the argument principle in order to count zeros inside a contour. I wouldn't be surprised if people did it. I also wouldn't be surprised if it isn't that frequent, because I think the geometry is actually more complicated. But nonetheless, and then with Roche's theorem in particular, we can find another proof of the fundamental theorem of algebra. Now, once you have one proof, a theorem, of course, is proved and established, but different proofs can shed different light on why a certain theorem is true. And finally, residues can be used to invert Laplace transforms. That's the final part of this presentation. On one hand, that means there is maybe an alternative to using tables. I don't do Laplace transforms on a day-to-day basis, and of course, if I had to, I would probably use a computer anyway. But it is also a tool when you've got a really complicated Laplace transform. And we're going to see in the final example of this presentation a situation where we have a really complicated function whose inverse Laplace transform we can still compute. Okay, so let's start with the argument principle. We've talked a lot about functions that are not analytic anymore, and so we want to call a function meromorphic in a domain D if and only if at every point in the domain the function is analytic or it has a pole. So these meromorphic functions are less well behaved than analytic functions, but they at least avoid these very complicated essential singularities. We also want to talk about the winding number, and this definition will take a bit. And we're going to look at a picture on the next panel. So we take a meromorphic function that is meromorphic inside a contour and analytic and non-zero in the neighborhood of the contour itself. So we want to stay away from zeros and from poles on the contour itself, and we will see in the picture ultimately why we want that to be. We want W0 to be a point on the contour, and we want phi0 to be a value of the argument of W0, and we want W0 to be a point on the image of the contour here. And now we want to let the point W start at W0, and we want it to run continuously once around the contour f of c in the orientation inherited from C. Remember, when we've got a contour, we can parameterize it, and we can stick that parameterization into f in order to get a parameterization of f of c, and that gives us then a way to traverse the contour f of c, and that's how we want to follow this point W around, and we want it to continuously traverse that contour. Well, then the argument also varies continuously with W. That means we may have to jump from one branch of the argument function to another, but that's not a problem, and lowercase arg is the multivalued function anyway. And so we denote the value that argument of W assumes upon the return of WZ by phi1. So basically the image contour just goes around, ultimately comes back, and whatever value the argument has at that stage, that's phi1. And well, then the difference phi1 minus phi0 is 2 pi times the number of times that the image contour wraps around. And here is where, if you don't have the picture in your mind, this one becomes really hard to read. Remember, we're going to look at a picture. But we set delta of the argument of f of z on C to be phi1 minus phi0, and the winding number of f of c around the origin is 1 over 2 pi times that delta c arc f of z. Okay, so what does that thing mean? Let's visualize it. we start at some point z0 in the domain, and we have some kind of contour C that just need not wrap around anything in particular. So in particular, it need not wrap around the origin at all. It just sits somewhere. But we typically want it to be simple and closed. And then our function f takes this contour and maps it to its image. And so z0, for example, goes to an image point. And let's just say that that image point is our w0, so that's our starting point. And now if we follow along a parametrization of the original contour around this whole thing, well, we can plug that parametrization into f, and that would mean as in the domain we follow the original parametrization, we follow the parametrization of f of c in the range. So if we take a little step in the domain, the image parametrization takes a step in the range. We take another step in the domain, we take another step in the range, take another step in the domain, take another step in the range. Of course, this is actually going continuously, right? As this thing smoothly moves along, the image also smoothly extends. That's something where I just didn't have the time, and admittedly, at least currently, not the skill to set that up. At least I didn't think of doing that. But we can see basically as we go in the pre-image, we also start drawing the image contour. And what we can also see is that as we, in this example, have gone halfway around the domain contour, the original contour, the image contour has gone once around the origin. Okay, so we keep going, and the image contour keeps wrapping here in this example, and ultimately the one thing that must happen is that as the original contour gets back to z0, the image contour must get back to f of z0. Okay, well, there are some things that are happening here that are not a problem at all. For example, the image contour is intersecting itself. Well, f need not be injective, so that's not a problem. The one thing that must happen, however, is that the image contour must go back, and in this case, we can see it's sensible to say that this image contour wraps twice around the origin, right? Because that's basically what geometrically is happening. And in this figure, if we're looking at the argument, if we start here, well, by the time we've gone around once, the argument has increased by 2 pi, and if we go around another time, the argument has increased by 4 pi, and so that's what that delta c of the argument of f of z is about, and if you divide that by 2 pi, you get the number of times things have wrapped around. This also explains why we don't want to have poles or zeros on this original contour, because if we had a 0, this image contour would go through the origin, and then it's not really clear if it wraps around on this side or on this side, because indeed it does neither. So the winding number would be undefined. And similarly, if there was a pole, well, then the contour would go off to infinity, and we also wouldn't know how something wraps around the origin that goes off to infinity and then comes back. Okay, so the theorem, which is called the argument principle now, says the following. We take a positively oriented simple closed contour, very much like in the picture we had on the previous panel. We want f to be meromorphic in the interior of the contour and then analytic and non-zero in the neighborhood of the contour itself. We want z to be the number of zeros of the function in the interior of the contour, and that's counted with multiplicity. We're getting used to that by now. The multiplicity plays a role because that affects, of course, the powers in the power series expansion. And let p be the number of poles of f in the interior of C, which are also counted with multiplicity or counted by the order of the pole, right? We could say with some slang, I guess, that a pole of order m has multiplicity m. And what happens then is that 1 over 2 pi times the delta c arc f of z, so the winding number of f along the contour f of c around the origin, that is the number of zeros in the interior minus the number of poles in the interior of the original contour. So it's important to keep track of what's happening in the original contour and what happens and what is the image contour. We're going to see that that's also important for the proof. What we will do is we will evaluate the integral of f prime over f along c in 2 different ways. That makes a certain amount of sense because f prime over f, if you take the antiderivative, that's the logarithm, and the imaginary part of the logarithm is the argument. And on the other hand, f prime over f is also something that you can evaluate with the residue theorem, and the zeros of f will be poles of this function, and the poles of f will, I think, still be poles of this thing. We'll see how that goes precisely as we do the computations. So we take a parametrization of the original curve C, but we immediately jump to the image and we look at f of z of t, and we turn that into rho of t e to the I phi of t, and we want that to be the polar representation of the image curve f of c. Okay, let's compute. The integral over the contour of f prime over f is the integral from a to b, f prime of z of t over f of z of t times z prime of t. That's just the definition of the contour integral. If we evaluate that, well, if we start working with that, we realize f prime of z of t times z prime of t, that's by chain rule the derivative of f of z of t. Okay, now I've got f of z of t here, and I also have f of z of t here, so I can replace that with that polar representation, which is what happened here, at least in the derivative. So this is 1 over f of z of t times the derivative of the polar representation. And now I can say that's 1 over the polar representation of f of z of t times this derivative, which I compute, of course, with the chain rule. So this is chain rule product rule. So this is rho prime of t e to the I phi of t plus I rho of t e to the I phi of t phi prime of t. Derivative of the first times the second plus derivative of the second times the first. Straight product rule. Okay, now I can, I think, puzzle those apart. And on one hand, if I take this first term here and divide it by this denominator up front, I just get rho prime over rho. And if I take the second one, I get that the rho of t e to the I phi of t, that cancels, so I just end up with I phi prime of t dt. And if I integrate that, I get ln rho of t in the bounds a and b plus I phi of t in the bounds a and b. And, well, the radius will be the same on both sides, so that'll be 0 plus I times phi of b minus phi of a. And phi of b is the phi 1 that we had, and phi of a is the phi 0 that we had. And so this is I times the delta c argument f of z. And on the other hand, the integral of f prime over f along c is 2 pi I times the sum of the residues of f prime over f at the singularities inside c. And we're just going to compute those residues now. So if f has a 0 of multiplicity m0 at the point z0, well, then f of z is, as we know, z minus z0 to the m0 times g of z for some g that is analytic in the neighborhood of z0 and which satisfies that g of z0 is not equal to 0. So that means that f prime of z over f of z is, well, you just take this thing and take the derivative with the product rule. So derivative of the first, m0 z minus z0 to the m0 minus 1 times the second, g of z, plus, this is not a quotient rule, right? We're just taking the derivative of the numerator, plus the first, z minus z0 to the m0 times the derivative of the second, which is g prime of z, divided by, well, f of z, z minus z0 to the m0 times g of z. And now we start simplifying that. I think we'll just break up the fraction again. If we cancel in the first fraction the g of z and the z minus z0 to the m0 minus 1, we just end up with m0 over z minus z0. And in the second one, if we cancel the z minus z0 power, we end up with g prime over g. But now that means that the residue of f at z0 is m sub 0, because remember, g is analytic and non-zero at z0, which means this thing is analytic, so it has a residue of 0. And by definition of the residue of this thing is m0. If f has a pole of order mp at zp, well, then f of z is z minus zp to the negative mp times h of z for some h that is analytic in the neighborhood of zp and satisfies h of zp not equal 0, right? This is something that we've certainly worked with quite a bit when we did the calculus of residues. Anytime we have a pole, we can factor out the appropriate power of the z minus the place where the pole is, and we end up with an analytic non-zero function for the rest. And we do exactly the same thing. We look at f prime over f, and again we get, well, with the product rule in the numerator, derivative of the first, negative mp times z minus zp to the negative mp minus 1 times the second h of z plus the first z minus zp to the negative mp times the derivative of the second h prime of z divided by f, which is z minus zp to the negative mp h of z. And now we do the same thing. We break that fraction up. So we end up with, if we cancel the h and as many powers of z minus zp as we can, we end up with, well, z minus zp to the negative 1, if you will, and so that's 1 over z minus zp. And of course we keep the negative mp, and that's what we have here. And for the second one, we just cancel the power of z minus zp and end up with h prime of z over h of z. Again, this thing is analytic, and by definition of residues, the residue of f over f prime, not f. Yeah, okay, let me fix that real quick in this slide. Yeah, and we're back. It's the residue of f prime over f, of course, not of f itself. I apologize for the typo here and here. It's interesting. I already proofread those slides actually several times, but when you talk your way through it, you sometimes still see more. Well, either way, those are the residues. And so that means that I times the delta c arc f of z, which is 2 pi times that winding number, well, times I, that's the integral of f prime over f along the original contour c. And we know that that by the residue theorem is 2 pi I times the sum of the residues at the singularities inside, and that's got to be another f prime over f. Right, so that's the sum of the residues of f prime over f at the various singularities that we have there. And that is 2 pi I z minus p, because we've just seen that basically the residue of f prime over f at a 0 of order m0 is just m0, and the residue at a pole of order mp, if you will, is just mp. So that means that that sum really is 2 pi I times z minus p. And if you now just divide by 2 pi I, you get the argument principle. All right, and that is the requisite equation, right? So that finishes the proof. Let's take a look at how this works. Basically, here's a question that at first looks almost unanswerable, right? How often and in what direction does the image of the circle z absolute value equals 4 under f of z equals sine of z wrap around the origin? I mean, what are you supposed to do? Find a ruler and a compass and then look at how this very complicated function deforms this contour? Well, if you've got really good visualization, if you need something like that, you may want to try it, but here, with the argument principle, you just realize that the sine function has no poles, and it has 3 zeros inside the circle z absolute value equals 4, and they are, of course, pi, negative pi, 0, and pi, and they're all of multiplicity 1. And that means by the argument principle, the image of the curve wraps 3 times around the origin, and it goes in the mathematically positive direction because you get a plus 3. If you apply the argument principle, you get a minus 3. That would mean it would go in the mathematically negative direction. And that's it already. Okay, so that's how the argument principle works. Let's take a look at what is called Rouché's theorem. Rouché's theorem says that if you have a simple closed contour, and f and g are both analytic functions inside C and also on a neighborhood of C, and if we have that the argument of f, the absolute value of f is greater, strictly greater than the absolute value of g for every point on the contour, then f and f plus g have the same number of zeros in C counted with multiplicity. Now that sounds like another one of those, well, you do mathematics for mathematics' sake, but remember that finding zeros, locating zeros, is something that is very important whenever we're solving equations. Locating zeros of denominators was important for the residue theorem to determine how many singularities there were inside a certain contour, for example. And so this is something where then basically if you do the adding and or subtracting the right way, you can count the zeros inside a certain contour for a complicated function by looking at a simpler function. And that's what our examples are also going to show. First, of course, we have to determine why that result is true. So by the argument principle, we have that the number of zeros of f plus g is 1 over 2 pi times the change in the argument of f plus g along the image of the contour C. So that would be the change of the argument along the contour f plus g of C, actually. And now we just do some algebra inside, because the function f of z plus g of z is the same as f of z times 1 plus g of z over f of z, right? And that's, we want f of z to be strictly greater than the argument of g of z in particular, the absolute value of g of z in particular. That means f is strictly greater than 0 in absolute value, which means we can do this division on the contour C. And now we can break that apart, because the argument turns out to be multiplicative, and that's something that comes pretty much from the properties of the logarithms. Or you could just realize that these arguments, of course, are e to the I theta 1, e to the I theta 2, and if you put that together, you get e to the I theta 1 plus theta 2, and that's the separate arguments, right? So we can break up these changes in the arguments to look at f of c as well as at 1 plus g of z over f of z. And on one hand, well, this is the number of zeros of f inside the contour C, and that's because both f and g are analytic and don't have poles, therefore, so that's just the residue, the argument principle applied to 1 over 2 pi times this delta c arg f of z. And the other one I left like that because we're going to claim that that's 0, and that's another one of those arguments where we use inequalities. Basically, we're going to show that this function stays so close to 1 that it can never wrap around the origin. And if you want to show something stays close to 1, well, you form the difference to 1 and do that in absolute value. Well, so 1 plus g of z over f of z minus 1 absolute value, that's just the absolute value of g of z over f of z, and that is smaller than 1. Well, that means that the image of c under the function g over f lies in the disk w minus 1 smaller than 1, right? The distance of this thing from 1 under the function 1 plus g over f, actually. Yeah, so the image of the curve under the function 1 plus g over f stays in the disk around 1 that has radius 1, and it's the open disk. And so that means, in particular, the image does not wrap around the origin, right? If you stay closer to 1 than 1, you can never go past 0 anywhere. And that means the last term above is 0, so that term here is 0. And that means the number of zeros of f plus g is equal to the number of zeros of f, just as Rouché's theorem claims. Okay, how does that get applied? Well, we can, for example, try to determine the number of zeros of the polynomial p of z equals z to the 4th plus 4z squared plus z plus 1 inside the circle around the origin of radius 1 and inside the circle around the origin of radius 4. And basically this is now a lot of application of the triangular inequality as well as the reverse triangular inequality. And well, here we go. We just have to break things up right. So on the circle z absolute value equals 1, we have that 4z squared absolute value. Well, realize when everything has size 1, this term ought to dominate, right? Because that's 4, and these other 3 can add up to at most 3. So on the circle z absolute value equals 1, you get the idea that you want to talk about 4z squared because that's the biggest guy here. That is equal to 4, and that's greater than 3, which is greater than or equal to z to the 4th absolute value plus z absolute value plus 1 absolute value, which by triangular inequality is greater or equal than z to the 4th plus z plus 1 absolute value. So that means if you're using Rouché's theorem, the function p of z equals z to the 4th plus 4z squared plus z plus 1 has the same number of zeros inside that circle as the function f of z equal to 4z squared, because you use f of z equals 4z squared and the rest is your g. And f of z equals 4z squared has 2 zeros there. Remember that we have to count things by multiplicity. So that means there are 2 zeros inside that small circle. Let's take a look at the circle z absolute value equals 4. And basically the way you analyze it is, again, you want to find one term that's dominating. And when things are equal to 4, well, 4 to the 4th is 256. That's a lot bigger than this stuff can get. That's at least something that I would hope at some point in time with enough number sense we can do by feeling, if you will. But and then, well, we just work it out with of course a chain of inequalities. If the chain of inequality doesn't work, then our feeling was wrong. Well, too bad, then we just have to start over again. So here z to the 4th absolute value will be 256, because 4 to the 4th is 16 squared, which is 256. 256 is greater than 69. How did I get that number? Well, I looked at the rest and tried to estimate it. So this is no magic. This is just working from the other side and then putting things together. And 69 is greater than 4z squared plus z plus 1, because, let's see, 4z squared plus z plus 1 is smaller or equal than 4z squared, absolute value, which is at most 4 times 4 times 4, which is 64, plus another 4, adds up to 68, plus 1, which would be 69. So z to the 4th is greater than the rest in absolute values, and that means with multiplicity, this polynomial has 4 zeros inside the circle z absolute value equals 4, because z to the 4th has 4 zeros there, and that is the term that dominates, and we realize that the term that dominates has as many zeros as the sum. That's what the Rouché's theorem says. All right, another example. Yeah, we want to do a new proof for the fundamental theorem of algebra. All right, so take a polynomial. Remember, what does the fundamental theorem of algebra say? It says that a polynomial of degree n greater or equal than 1, complex polynomial, of course, has n zeros. All right, so if the thing has degree n greater or equal than 1, then an is not equal to 0. Well, then p of z is anz to the n plus an minus 1 z to the n minus 1, and so on, all the way down to a0. And we can factor out an. Well, that just gives us quotients with an, that's fine. But now for c sufficiently large, on the circle z absolute value equals c, we will have that z to the n is just c to the n, and that's going to be greater than this number, which is fixed, times c to the n minus 1, plus c to the n minus 2 times its coefficient, plus c to the n minus 3 times its coefficient, and so on and so on and so on. So in particular, c would have to be greater than the sum of the absolute values of these quotients, I guess. But that can be done. And so that's where in analysis sometimes we have that leeway. If it can just happen on a sufficiently large circle, we're fine, and we don't necessarily specify how large that radius has to be. But what does that mean? That means z to the n absolute value is the dominating term. So that means, because again by triangular inequality it's bigger than the absolute value of the sum of the remaining terms, and that means by argument principle p has as many zeros as this dominating term, and that dominating term has n zeros counted with multiplicity. They're all at the origin, and that proves the fundamental theorem of algebra. Okay, this is a good time to take a break, and well, I probably should. I might just record the inverse Laplace transforms right after this, but you probably want to do this too, because this is the geometric part of the presentation, and from here we're then going to focus on, well, stuff that is also geometric, but which entirely connects to the Laplace transforms, and which gets rather deep algebraically. So I'll see you in a couple of minutes or later after you've done some homework on the argument principle and Rouché's theorem. I'll see you then.